Day 10 of the advent of Code 2024 brings some graph theory. The problem statement says there is a map with each digit representing the height of the terrain at its place on the map. The task is to find and analyze hiking trails. From any cell on the map we can step to the left, right, up or down. Each next cell on the hiking trail must be 1 unit higher than the preceding one. These are 2 hiking trails. Here is one trail and here is another. Trails start at 0 and end at 9. Our task today is to analyze these hiking trails. Here is a bit larger map with a handful of trails. The total number of trail endings starting in a single trailhead is that trailhead's score. We must sum up all such scores on the map. Here is how I will solve this problem. Some nodes on the map are connected. We can step from this node 8 to the neighboring node 9. I will now implement an algorithm that forms the trails out of those neighboring nodes. So far I have only loaded the matrix of digits. I need a few helper methods. This one will return all points on the map that contain 0. Look how nicely link comprehension helps with a multidimensional problem. Addressing a point on the map with a tuple. Another method for testing whether a point is inside the map. Then testing whether a step on the map goes uphill, and then binding these together. Returning a sequence of all uphill steps from a given point. Fundamental methods like these are always helpful. This is the central method we must write. It will find all the steps heading from a given trailhead. Here is how the algorithm goes. There will be a data structure that records the places we have yet to investigate. Using a queue for this purpose makes this a breadth-first search algorithm. A stack would make this a depth-first search algorithm. We start the search from the trailhead. We shall then discover all other reachable points on the map. Another very important detail is the cache of known locations. We shall use that to avoid investigating the same location multiple times. The algorithm runs while there are more places on the map to investigate. Dequeue the new current point, mark it as visited so we don't investigate it ever again. Now how do we avoid it the next time? The add method on the hash set returns false if it already contains the value. Then we know we were here already, so we can immediately continue to the next item in the queue. This optimization makes the algorithm run in time proportional to the size of the map. Otherwise, we produce the point on the output. Every point will therefore appear on the output precisely once. Then comes the very last step in the algorithm. We search for the uphill neighboring points. We walk through all of them and then queue them for processing. With this, the algorithm is complete. You can learn more by researching how to construct a transitive closure. As for this problem, it only remains to calculate the result. For every trailhead, we must calculate its so-called score. That is the number of summits we can reach from that point. Walk from the trailhead obtaining all the reachable points. Then count those at height 9. Code almost writes itself when you bring it to this state. Let me show you that effect one more time. For the total score, get all the trailheads and then sum their scores. Part 1 is done. This is one elegant implementation of the breadth-first search algorithm. You will now learn how to augment it to start counting distinct paths. That is what part 2 of day 10 is requesting. We are still following the paths. But this time we observe that there are 2 ways to arrive at the point 6 here. Hence, there are 2 ways to walk down towards point 8, plus 1 additional path that branches from here. That makes a total of 3 distinct ways to arrive at the point 9 below. We must count distinct trails from every trailhead before summing up those counts. There is a critical observation to make. Unlike the general case in the graph theory, all paths going to one junction are the same length. The breadth-first search algorithm will process all predecessors of every junction on the trail before processing the junction node. Only under that assumption will my implementation be correct. Keep that at the back of your mind. I plan to keep track of counts as we progress down each trail. Instead of tracking visited nodes, we shall track the count of trails leading to each node. The hash set will not suffice anymore. The dictionary will map each point to its count. We already know there is one way to get to the starting point. And then it begins. We won't be skipping the nodes this way. We shall decide which nodes to skip as we count the trails. For instance, if there is already a count for the neighbor, we must have seen it before. Due to the growing nature of the trails in this problem, that neighbor must still be waiting in the queue. We shall only add the current node's counter to all other trails that led to that neighbor but not include the neighbor again. It is already waiting for its turn somewhere in the queue. Otherwise, this is our first touch with the neighbor. Initialize the neighbor's count to what the current node has, then enqueue it for processing. The new algorithm is complete. It will only take me a moment more to augment the return type. The method now returns all reachable points on the map, along with how many ways there are to get there. I need to fix the caller, but that is just a detail. This expression will continue to calculate the score for each trailhead. Part 2 requires what it calls a rating. That is just the sum of counts of all trail endings starting from one trailhead. Let's get it done. Walk down all the trails. Select their endings only. Sum up the counts. One line of code remains. For all trailheads on the map, sum up the ratings. This is the complete optimized solution to the problem of identifying and counting all the upward paths on a map. It runs in time proportional to the size of the map. There is no asymptotic complexity better than that, I can assure you. You can download this code for free by visiting my Patreon page. There you will find up-to-date instructions on getting the solutions for all 25 days of Advent of Code 2024 for free. You can also stay around and watch more advanced videos on C# on my channel. The day 10 is over and we can move on to solving the day 11.